Okay, so it says consider the function f of x equals 3 over x minus 2. What is that denominator telling you about the graph? You have a vertical asymptote at x equals 2, and we can see that that matches with what they've graphed over here. So, can a limit exist at a vertical asymptote? No. However, we can say that one-sided limits are equal to either infinity or negative infinity. So that's what the next thing is going to do. Now, if this is open-ended, you could still say D and E, but this is most likely going to be multiple choice, in which D and E is not an answer choice and positive and negative infinity are, and you got to figure out which one it is. So looking at the graph, I think is the easiest case, because you're saying, oh, okay, as limit approaches 2 from the left, okay, 2 from the left would be down here, so that's negative infinity. What about 2 from the right? Positive infinity. See how it's going up and up and up and up. All right, so that's great. So what happens when you're not given the graph? This is where you gotta kind of think about, well, what does it really mean? What is a number that's approaching 2 from the left? Like, what's a number that's barely less than 2?
1.
1 is less than 2, but it's not barely less than 2. 1.999. Okay, so what I'm going to do is I'm going to go 3 over 1.999. The more nines, the better you are. Okay, 1.999 minus 2. Is that positive or negative? Negative. Okay, it's also a really small number, and when you do 3 divided by a small number, you get a really big number. So this is numerically a way you can come up with the limit. And we're going to practice this again. Okay, what would be a number that's just barely more than 2? 2.001. So this is going to give you a positive result, right? And again, you're still doing 3 divided by a teeny tiny number. And so you get positive infinity, and you don't have to write the plus. I just did on that one, but you don't have to. By not writing plus, it's implied positive, as always. Okay, so that's what an infinite limit is. Okay, like we just said, these limits actually don't exist. Okay, but we can say that a one-side limit tends towards positive or negative infinity. All right, so let's practice this. On A and B, you're not given a graph, so let's do the number thing. First of all, do we have a vertical asymptote? We really should check this first. At 1, right? You look at the denominator for that. That has to be true for us to even say that these next two answers are going to be infinities. Okay, because otherwise we'll just do it like we did any other problem. So a number that's just barely less than 1 would be 0.999. And you may, as you practice this, not need that many nines, but for now I think it really brings home the point of what we're doing. Is this a positive or negative? It's a negative, so negative infinity. It's 1 divided by a teeny tiny negative number. So it makes a really big negative number. What do you think the next one is? Why? Yeah, if you pick a number bigger than 1, you get a positive result. Do you think there's always going to be like where one's negative and one's positive? I mean, always is a scary word, right? In math, it's like, ugh. Okay, let's look at the next one. You'll answer that for me in a minute. So on the next one, again, let's pick 0.999 minus 1. This time I'm squaring it, right? Because that's in the problem. Is this result positive or negative? Positive. And next time you see a problem with the squared, you could tell, hey, that's always going to be positive, right? The inside, the denominator anyway. So they're both positive infinity. What this looks like on a graph, by the way, is like when you are going up on both sides of a vertical asymptote like this. Remember something called multiplicity? You have an even degreed term. It's going to cause the same behavior on both sides of the asymptote. That's just kind of reinforcing this idea. You didn't have to think of it that way, but it might help understand it. Okay, what about C? It's a graph, so let's not be hard on ourselves. One-sided limits here are either positive or negative. One's positive, one's negative. Which one is the negative infinity? The bottom one, the right side. And this one's positive. This is a negative infinity down here. This is positive infinity up there. What about D? Both negative, right? Both going down, so both negative. So the graphs, I think, are a little bit easier. Okay. There's something, yeah. So this says, if f of x tends towards infinity or negative infinity, in other words, if the one-sided limit is infinity or negative infinity, what can we conclude about that line? It's a vertical asymptote. And I'm going to be specific with vertical because we are going to talk about horizontal asymptotes in about 5 minutes. Not quite 5 minutes. Okay, so let's turn the page. So if we have to have a vertical asymptote, we have to actually be really good at being able to tell if the graph has them. And we're not going to graph any of these. We're going to do these algebraically. So first look to see if anything cancels. If it doesn't, set your denominator equal to 0 and factor further if you can. From here, you're going to set each factor equal to 0, and that's how you get your vertical asymptotes. It's just a kind of a quick review of how to do this from what you learned before this class. The 2 is actually not causing a vertical asymptote. It's just a number. If it had been 2x, well, then I would have to deal with it. Okay, what about B? Nothing cancels, but does the denominator factor? It's tricky. It doesn't actually factor. Difference of squares factors, but sum of squares does not factor, and I'm going to show you why. Let's subtract the 16 over to the other side. We get x squared equals negative 16. Then we square root. What are we creating here? Imaginary number. And the good thing for us is we do not deal with imaginary numbers in here at all, ever. So we can say, what are the, there are no vertical asymptotes. We're not going to really focus on the trig for right now. I'm going to do that another day when we have more time. What do you think we need to do on D first? We got to factor this thing. So this factors into x plus 5 and x minus 3 and x plus 5 and x plus 2. You don't have to be as fast as me, but you just need to be able to do this accurately and somewhat quickly. Okay, now if a term cancels, you got to do that. Do you know what's causing that? A hole. Okay, so that's not a vertical asymptote. This x plus 2, though, is causing a vertical asymptote at x equals negative 2. So I already know the next question, because I've done this enough. What is this? What is the x minus 3 doing? It's not a hole, it's not a vertical asymptote, it's a root. It's an x-intercept. And this is something, it's like, it makes sense if you think about it because it causes the top to be 0. You know what though? We're not going to be dealing with x-intercepts. So at the end of the day, I don't care if you remember this. I care if you remember how to analyze the denominator between holes and vertical asymptotes. So this kind of recaps what we just said. A vertical asymptote is something that you cannot cancel. Okay? A hole is something that you can cancel. So here's how you know always the difference between the two. You first of all, you factor. If you get something to cancel, like in this problem we did, then at that x value, I mean, and each time I'm not showing this, but we're looking, that's the factor, and we're looking for the x equals, set it equal to 0 basically. This is a hole, otherwise known as a removable discontinuity. When you think of the word removable, just think cancel. We canceled it. Now, is there anything left in the denominator? No. So there is no vertical asymptote in this problem. And again, whatever's left in the numerator, that's causing an x-intercept, which is neither here nor there when we're dealing with limits. So here's another way of asking that same question. Determine whether the function has a vertical asymptote or a removable discontinuity, which remember is a hole, at x equals 2. So what are you guys thinking? What should we do here? Factor? That sounds good. I mean, that's what we've been doing on most problems. There is another way to do this problem, but I think factoring is the easiest way. So x plus 5, x minus 2. So since x minus 2 cancels, then what's happening at x equals 2? A hole, or a removable discontinuity. Just for fun, what's the vertical asymptote? Yep, x equals -5. Okay, so I feel like we've kind of exhausted the vertical asymptote situation. Let's talk about horizontal asymptotes now. The answer here would be hole removable discontinuity, because it said determine whether the function has which one at x equals 2. So I just put this in there as extra. All right. Now, do you remember your horizontal asymptote rules? Got low over high, 0 over y, high over low, slant you go, degrees are the same, play the coefficient game. And there are other ways to do that. There's something called Bobo, Bot, and Betsy, if you've ever heard of that. So if the rhyme is not working for you, I can teach you something else. But however you do, I want you to think, when you think horizontal asymptotes, you got to think limits as x goes to infinity. Think about what a horizontal asymptote does. It causes the graph to level out. So as x gets bigger and bigger and bigger, the y value is getting really close to wherever that horizontal asymptote is. This is why you studied horizontal asymptotes, to do these kinds of problems. So in case number 1, and keep in mind this is as limit as x approaches infinity, that's when you do horizontal asymptotes. Okay, look at the degree on the bottom is bigger. So which rule do we have? Low over high, 0 over y, 0. I mean, there's variations on the rhyme, so I might not be saying it exactly how your teacher did. But if the degree on the bottom is bigger, that horizontal asymptote and infinite limit is 0. Okay, what if the degree on top is bigger? What did you guys say? Slant. Well, think about what a slant does. It goes up and up and up and up and up and up and up, and now we call up and up infinity. So right here, your answer is either infinity or negative infinity, and the way you're going to decide is through common sense. If you plug a really big number in for x, like 1 billion, are you going to get a positive or negative result from this problem? Positive. What could I do to it to make you get a negative result? Put a negative in front of the 2x squared. I could say as x approaches negative infinity, that might change it. I don't want you to memorize anything else. I just want you to think, if I plugged in a really big number, what would I get? Would I get a big number or a big negative number? Okay, so then we look down here at the degrees are the same. This is where you play the coefficient game, 2/3. And the reason this works is because the top and the bottom are both growing at the same rate. Okay, notice real quick, I'm going to show you this. Notice that these numbers never ever, we didn't even talk about them. Okay, so like when we're looking at A, just cross them off. All you're going to look at is the highest degree part. Those degrees are the same. So what's our answer? 3/9 or 1/3. Okay, so again for part B, I'm going to just cross off the -10. And I have the denominator is the biggest degree. So that equals 0. Okay, what about C? The top is bigger. So is the answer infinity or negative infinity? Which one makes sense for this problem? Infinity. If either the 5 or the x had been negative, not both, but if one of them had been negative, our answer could have been negative infinity. Okay, then we get to D. This is where it gets fun. Square root of x squared. What's the degree? 1. Okay, it doesn't really simplify to x to the 1 power, but it helps you understand the degree. And since the degrees are the same, you play the coefficient game, which is a 1/1, so your answer is a 1. All right, cosine, real quick. Cosine goes up and down and up and down. It only goes as high as 1 and as low as -1. So it really isn't going to play any, it's never going to get big. Cosine of 1,000,000,000 is still between -1 and 1. So I'm going to scratch it out, which is really good news that we don't have to deal with it. So what's the answer? 1. Because the degrees are the same, the coefficients are both 1. 1 divided by 1 is 1. Okay, part F, same situation, sine. It doesn't matter how big x gets. Sine is always going to be between 1 and -1, so it's not going to affect the limit as x approaches infinity. And now we have an x in the bottom but not the top, so that infinite limit / horizontal asymptote is 0. All right, number 9, last one. Sine of 2x. How big could this one get? Anybody know? It still is only going to get as high as 1. Okay, so we're still going to scratch it out. We're going to put a 1 in its place. And even if it could get big, is it going to grow as fast as x? No. So that's also a 0. And then this is really the best advice of this whole page. When all else fails, think about plugging in a really big number like 1,000,000,000.